Hi all, this is Ashwin Muthraman here, going to explain one of the algorithms that is useful for finding the minimum cost spanning tree of a graph. Welcome to the graph lecture series, and we are going to see about Prim's algorithm today. So this is one of the algorithms to find the minimum cost spanning tree. I'll just give a short description of what a spanning tree is. So a spanning tree is nothing but a subgraph of the main graph G, V of E, G of V comma E, where all the vertices should be present in the spanning tree and it should be a tree, meaning there should be no cycle in the graph. Even though the graph has some cycles, the spanning tree should not have a cycle. Now, since the graph has weighted edges, we expect the final spanning tree to have the minimum cost of traversal between all the edges. So that is the problem statement of minimum cost spanning tree, and we have the Prim's algorithm here. Let me go through this algorithm and we'll have an example walkthrough also. So first, the algorithm starts with minimum cost edge. So out of in the graph, so we will first take the minimum cost edge. Okay. Now consider the edges incident on. So this edge is from Vi to Vj, right? Now we have to consider all the edges incident on Vi and Vj and add it to a particular list. Meaning that, so if at all I am taking this edge A comma B, this is not the edge that I am going to consider because this is going to be the minimum cost edge that I should take. For example, if I am taking any edge, I am just explaining step number 2. So if I take AB as the edge, I need to get the neighbors of A, get the neighbors of B, all the edges of that, and then I'll add it to the list. Okay. And then find the minimum cost edge from the above. We are going to find the minimum cost from the above list. And then if it forms a cycle, we are going to discard it because we don't want a cycle. That's the basic definition of spanning trees, right? And then if it does not form a cycle, we'll add it to the spanning tree, that we'll obviously do, and delete it from the list because we are not going to consider the edge again. Next, repeat steps 2 and 3 until n-1 edges are formed, because if there is no cycle in the graph and it is to be a tree, then the number of edges should be equal to n-1, right? And then we have to repeat these steps until n-1 edges are added to the spanning tree. Now let me go through this example, right? So let us start with this, the minimum cost edge. So out of all this, there is only one minimum cost edge. If there are more than one minimum cost edge, we can take any of the edges. Now here, without any ambiguity, the minimum cost edge is going to be D comma E. So now let the spanning tree be defined like this. So the first definition of the spanning tree, first condition is that it should contain all the vertices. So I'll just write all the vertices here, and then we'll add on the edges based on the minimum costs according to the Prim's algorithm. Okay, so now the first edge that I'm going to consider is D comma E, and the list I'll keep it here. So the list that we are talking about is going to be here. Okay, so first I'm going to add DE because that's in all the edges we have that as the minimum edge. I'll just add this, put the cost as 1 here. Okay, next we are going to do this second step, consider edges incident on Vi, Vj. So now for D comma E, now I've considered the edge DE. What are all the edges incident on DE is BD, AB, CD and EC. So there are 4 edges, right? And on this there are only 2 edges, DE and then CE. So now I'm going to add all the edges to the list. So let me add all the edges. BD I'll add here. I'll add AD. I'll add CD. I cannot add DE because that is already present. So for particular D, so VI I have written all the edges adjacent to it. For E I'm going to write all the edges. DE cannot be written because it's already considered. Now I'll just write CE. This is the list at step number 1. Above this, I'll just write the cost of each of the edges. BD costs me 2, AD costs me 3, CD costs me 3, and CE costs me 4. Oh, it's already sorted anyways, but yeah. Now, so find the minimum cost edge from the above, which is the minimum cost edge. BD is the minimum cost edge. Now check if it forms a cycle. If it forms a cycle, we'll discard it. BD, it does not form a cycle, so I'm just adding this to the array. Sorry, adding this to the spanning tree, and then write this. Then what it says, delete it from the list. So I'm just going to delete this from the list. I'll just delete this from the list and then create a new list now. So now the list will be changed as BD is deleted. Now we just have AD, we have CD, we have CE with costs 3, 3, 4. And now we are going to check what are all the edges incident on B, edges incident on D. If you check the edges incident on D, that we have already written, so we need not reconsider it. If you can also, you can do BD is already added, AD is already there in the list, CD is already there in the list. No, DE is already added. Now just consider the B vertex. So for the vertex B, we have only two edges, AB and then BD. BD is already there, so we need not add it. We are going to add AB here. What is the size, what is the weight of this? This is going to be 2. Now among this, how do we find the minimum? Which is the minimum? Without any ambiguity, AB is going to be the minimum. Again, I'm going to repeat steps 2 and 3. Steps 2, I just added this, and then step 3, I'm going to execute it here. So I'm going to add AB here, and then going to write the cost as 2. Right? Now I have to delete this edge. I'm going to delete AB edge. Now how the list will be looking like? The list will be again looking like this. AD, CD, CE. This is not there. Again this will be 3, 3, 4. And now we have considered B and A. All the edges incident on B is already there present in the list or present in the tree. Now consider all the edges present going from A. So A as AD, AB, AC. There are only 3 edges. Now if you consider AB, that's already added. Now if you consider AD, that we can add it here to the list. AD. Okay, AD is already there, right? We need not add it to the list. Okay, so this is already there in the list, we need not add. Now we need to add AC alone, which costs me 5. This is the current list. Now from this list, take the minimum cost. If you take the minimum cost, I'm going with AD first. If I'm taking this as the minimum cost from this list, I'm going to delete AD. Okay. Now if you see, if it forms a cycle, if AD forms a cycle, is obviously because ABDA forms a cycle, then I cannot add it. So I'm going to discard it. Next minimum element in this, what will you find? You will find 3, right? So which is CD. Can we add CD? Yes, we can add CD here with the cost of 3, right? I'll just delete this and then add it. Now, do we have to consider all the edges from C and D now? No, because we have got this step, n-1 edges. There are A, B, C, D, E, 5 vertices. There are 1, 2, 3 and 4 edges. n-1 is satisfied, n-1 edges we got. So this is the final spanning tree. Let me calculate the cost of this. Cost will be equals to sum of all the edge costs, which is 2 plus 2 plus 3 plus 1, which is equals to 8. So you can draw all possible cases of the spanning trees and verify manually that this is the minimum cost spanning tree that can be possible from this particular graph. And this is what Prim's algorithm says. Now quickly going through the space and time complexity of this. Now instead of having this list and sorting it every time, we have a special queue called priority queues, right? So that we can use that data structure here for inserting and then finding the minimum element. So we have totally E number of edges, right? So if you consider a priority queue, insertion time into the priority queue is big O notation of log E and log N. In this case it's E, and again deletion is also log E. So basically you have the space, time complexity. Talking about the time complexity, for each of the edge that you are considering, this might have E number of edges associated with it. So it is E number of insertions or E number of deletions in the worst case. So the time complexity is going to be order of E log E, which I can also write it as E log N, right? Because E in the worst case, maximum of E might be equals to N into n-1 by 2. So just for the simplicity, I'm just writing it E log N. Now space complexity, if you look at the space complexity of this, you need to have a visited array because you cannot keep on adding all the vertices, right? So if this particular vertex is visited, because again and again we need not check. If D is already visited, we need not check its neighbors. So visited array is required. So it can be order of the number of vertices plus plus we need to store this list. This list can have a maximum of e, right? Number of edges. So this list also we need to store. So that is basically in the priority queue we need to store. The number of nodes in the priority queue can be at the maximum e. So space complexity will be order of n plus e. So this is the Prim's algorithm. We have covered the algorithm, we have covered an example and the space and time complexity of this, the analysis of complexity. Thank you.